Okay, folks. Okay, so the wiki has been set up. I guess most of you, several of you, actually only 4 more. I think we have about, no, in fact 2 more probably. Should still log in. Those of you who are registered should sign up here. Okay, I guess, and make sure that, and once to be able to do this, you would need an account which you should create for yourself. And once you're done, then I will disable the account creation so that I can basically, I don't want spam being there. Right? And then also, actually starting this week, we will start. You use this for a variety of things, including paper reviews. When before coming to the class, I might ask you to write short reviews of paper that you read, and also for other things, including your project proposals and so on. Okay. Okay. So today I am going to complete, hopefully, go forward with the discussion of automated planning. We were looking at the strips representation, the state variable representation, which has also been called the strips representation because strips planner actually used it first. Okay. And strips, and then we look at both the simple strips representation and some syntactic sugaring on top of it, including quantification and so on, and then compare that to atomic representations, which we started with, which is a state-based atomic representations. The one thing that I know that a bunch of you are essentially coming from Chitta's group or Ju Young's group, and in some sense you might actually be more interested in the other comparison, but you can supply it yourself. For example, what do you lose with strips representation that you might have with first order, but situation calculus representations, for example. I'll say a little, but you might actually have some ideas about that too. Okay, and then we'll talk about at least 3 different ways of setting up a search for finding plants, and that's more or less what we're going to do today. And then one other thing that I want to do is, I know that you're supposed to have read the chapters, and what I would like to do, now that I know who is going to be in the class, basically this is going to be the more or less the study group, what I would like to get some inkling of is, am I going too slow? Okay, I don't think I can go fast. I'm incapable of, I think people tell me that I go fast, but I don't think, I think this should have been done on the first day, but it's still there. So the question here is, am I going too slow for you? In which case, we can actually go far faster. Okay, so that's something that you can tell me based on your reading versus what's happening in the class. Okay, so we looked at problems with state transition models, the atomic models, and then state variable models, and then we looked at an example for one single example, that's the blocks world thing we looked at, and we also I jumped ahead and showed that the idea here is at least one simple way of understanding what does it mean to apply an action to a state, and that was we'll come back again, was this. So essentially, when you apply an action to the state, then you should make sure that it's the preconditions, which are essentially partial assignment of values to variables, those hold in the state in which the action is being applied, in which case the new state will have a partial assignment that this action provides. Partial assignment that action provides. That much is for sure, and then everything else, other variables for whom the action doesn't give any values, they just carry over from the previous state. This is in some sense the reason why if you apply the same action in multiple different states, what gets carried over changes. That's how you're changing the states. Okay. Okay. So that's where we were, and then so why is this strips representation slightly more compact? I mean, why is it better than atomic representations? One important idea is that actions are now going to be much smaller than S by S matrices, because in the atomic representation all actions are of the same size. They are S by S size. Okay. Here you can essentially have actions which can be quite complex but also can be quite simple. Okay, so if this action only cares about value of one variable and changes value of one other variable, you can do this with just one bit here and one bit here. Okay, whereas in the atomic there is no difference. It will still be the same same S by S matrix. Okay, now it's important to understand that if in fact we live in worlds where our actions essentially affect arbitrarily large number of propositions, I mean the state variables, then there isn't much of a difference between whether you are doing state variable models or explicit state models. And this is actually a very strong point. This is also true for first order logic versus relational logic. If there is no structure to be exploited in your world, then you may as well, there is not much of a difference between being in the relational and first order level versus being in the atomic level. The reason we believe these kind of representations help us is because we tend to believe that we live in worlds where actions tend to depend on a few of the many state variables and only affect a few of the many state variables. This is a strong locality assumption about what actions will change. Okay, that's important to understand that. So in state variable model, actions are represented only in terms of the variables whose values they care about and those whose values they affect. In the worst case, that might be all on this side and all on that side. In fact, the funniest thing is if I can pretty much take an S by S matrix, right? An S by S matrix, and just arbitrarily put, remember that, arbitrarily put zeros and ones to making sure that in each row there is not more than one, right? Because if there is more than one, that means it's a non-deterministic action. So if I arbitrarily put zeros and ones in this thing such that no row has more than one, and if I give you such a representation and I ask you to convert that into a strips action representation, in some cases the strips action might look actually quite baroque. Do you understand what I'm saying? So in some sense it might be applicable in a variety of states, and if you really think of these states in terms of state variables P1 to Pn, then you are essentially saying, since it's applicable in S1, S19, S55, S39, so you're doing a disjunction of all these conjunctions. That would be your precondition matrix. And then the effect states, again, you have to kind of, and in the case of the effect states too, you may actually have to split this action into multiple small actions, because in different cases it's changing different state variables. So even though we sort of go with this, it only makes sense because we believe that in our worlds there is a locality to the representation. Okay, that's what this is being said. Okay, and so we are started from atomic. We are now mostly will be spending time here, and some of you probably actually know how to represent actions in situation calculus. In fact, I mentioned this. We discussed this in 471. I may come to discuss this a little later here, but there is an interesting the situation calculus representations can be even more expressive. I mean, they have the same sort of advantage from atomic to relational as relational to first order. Okay, so some of the same arguments will hold up there too, but we won't talk about that right now. Okay, one other thing I want to mention is, so here in fact all the the one thing that I want you to remember is, even though we write actions in terms of propositional variables, okay, really you can write them in terms of multi-valued state variables, right? And so in some sense what you really want to say here is the preconditions and effects are partial assignments over variables. Partial assignments over variables. Okay. So this one is saying hand empty equal to true, clear x equal to true, on table x equal to true. Okay. Now, actually it turned out in all these actions, the preconditions were all quote unquote positive. For the propositional case, there are only, it's basically Boolean variables. And so for a Boolean variable, there are two values. There is no real reason to believe that one value is somehow better than the other value. But somehow we tend to think true is better than false. I don't know what the heck, why, really, okay? So because we tend to think true is better than false, we tend to actually, these particular actions, they're said to be positive precondition actions because they only have positive preconditions. That means their partial assignments over variables are all talking about true values for some variables. But there is nothing sacrosanct about that. I might have an action which requires a precondition that a certain variable be false. And the moment you actually get out of the propositional realm, then a variable can have 15 values, which is better. There is no better. So certain for the preconditions, there has to be, the variable has to have certain value, and the effects, I'm going to set certain variables to have certain values. Okay. The reason I bring this up again is, as you go and as you read any papers in planning, you tend to see this big distinction made between positive versus negative preconditions. In fact, even though I wrote the effects like this, in this particular case I wrote holding x is made true, clear x is made false, clear y is made true, and empty is made false. And in the original strips representation, which is more or less what you will also probably saw in the textbook, they would differentiate the positive effects and the negative effects. Positive effects are called adds, and the negative effects are called deletes. Again, very arbitrary terminology. There is no real reason to believe that giving a positive effect is somehow makes the action much more interesting compared to giving a negative effect. Okay? It really is a question of what is the problem. If in fact sometimes you might have a goal which is to make a certain variable have negative value and false value, in which case it's the quote unquote delete effects that wind up being useful. Okay, so get rid of, if you happen to have that by reading the chapter, get rid of this artificial importance of adds versus deletes. They're just basically values for state variables. And preconditions are a partial assignment, effects are a partial assignment. And if you think about that, then there's one more step which we'll do in a minute, which is basically supporting multi-valued state variables, which is like the de rigueur right now. Most implemented planners wind up using multi-valued state variable representations. It's no big deal. In this particular case, it's 2-valued. You can also do 3-valued, 15-valued, whatever. Okay, so the other thing that I also, we could do without changing much is to actually support effects and actions with essentially what look like conditional effects and quantified preconditions. Okay, so for example, I have this is a slightly different world where you have 2 packages on Earth and you are trying to take both of them to Moon, and you have a one-way rocket which can only be used once. Okay, and of course if you want to get both the packages onto the Moon, and I assume you realize that you have to put both of them in before the rocket takes off, because once it takes off it can't come back. Okay, so now if I want to write that particular world, okay, in terms of some actions, one thing you could for example do is, so loading of an object will require that the object is in the same location as the rocket, at which point the proposition in O1 becomes true. That means that object is now inside the rocket. And then in this case, unload, all it requires is that it's inside the rocket, in which case it's no longer inside the rocket. Okay, and then fly essentially is an interesting scenario where you can only fly, since this is a one-way rocket, it can only be flown if you are on the Earth. Okay, and then if you are on the Earth and you fly, then you are no longer on the Earth and you are on the Moon. Okay, you're on the Moon, and this looks like a nice little propositional formula. It's actually a first order formula. It's basically saying for all x, if x is inside the rocket, then x would be on the moon and x won't be on the earth. X won't be on earth. Okay, this is called a quantified conditional effect. Quantified conditional effect. So in one fell swoop, actually the things that you saw in this is, for example, you can have okay, so this one is actually, these two are simple actions like the ones that you have seen before, but this one now suddenly has a quantified conditional effect. Okay, but that's really kind of syntactic sugaring in this case, because as long as you happen to know, for these kinds of actions, if you are applying them in worlds where the initial state is completely specified, then the quantification is over finite worlds, and since you don't have any function symbols, you can essentially write it out as essentially a large big conjunction. Now what's more interesting, of course, is the conditional effect itself. So you might also have, you for example have in O1 implies at O1M and not at O1 Earth, right? Now the interesting thing about this is, this is a conditional effect. This is saying that I will have these changes to these variables only if this variable happen to be true. Again, I'm calling in O1, it looks like a predicate with the argument, but as I said, you can actually think of them as state variables, because once you ground them, they're essentially state variables which are true or false. Okay, now conditional effects are quite interesting. Did I mention to you that preconditions are funny things? Last class, that in fact an action with preconditions is a kind of a funny action, because what if I try to do the action even though its preconditions are not satisfied? What happens then? The world must come to an end, because then after that you can't do anything else, logically, because when the action should not be done, you did it, and so I don't know what happens after the action is taking place now. Okay, whereas, and I said in fact what I would like to really say, and I think my favorite example is trying to lift the thing. I'm actually executing right now, lifting of this table. The world still didn't end. Okay, the table just stayed where it is. Okay, so the way you could handle that is to have actions which don't have preconditions at all. They only have conditional effects. Anybody can try to lift anything. Okay, and if they have a lot of strength, then there is a conditional effect, which basically says when you have enough strength, then the table is airborne. Okay, so you could write conditional effects, and by writing conditional effects, you could avoid thinking in terms of this problem of what happens when you apply an action and the preconditions are not satisfied. Okay, actually, the interesting thing about preconditions is you'll see later on that if you could use a particular domain, you can either formalize it with actions with preconditions or model it with actions without preconditions, just only conditional effects. Okay, semantically this makes more sense, but for the planar search this makes more sense. Can you see why? Because those whose preconditions don't work, they don't even need to be applied, so they cut out some of the branches in the search. Okay, having preconditions actually makes reasoning about the plans and searching for plans easier. Okay, whereas having conditional effects makes for more graceful semantics. So that even when something isn't holding, the worst that this action will do is leave the world in its old place. That's what you say. Okay. One other thing you want to keep in mind is that can I have this, for example, an action A1, whose effects are, whose preconditions are P or Q, and an effect is R. Is that possible? Again, now that I'm thinking of this as the syntactic sugaring, can I allow that? Obviously, right? Because then essentially this action can be written as A11, which has P as the precondition, R as the effect, A12, which has Q as the precondition, R as the effect. It'll be the same domain model. Can anybody see this is actually true for the problem that we have been looking at, the specific planning problem we are looking at? This actually will fail for more general planning problems. Do you see that? So for example, imagine you're trying to use this action in a world where the initial state is not completely specified. That means you have uncertainty about the initial state. Okay, suppose I told you all you know about this initial state is either P is true or Q is true. I don't know which one. Then the original action can be used to still achieve R. After compilation, you can't use it, because the compiled actions will require, is P true? If not, I can't be used. Is Q true? If not, I can't be used. Do you see what I'm saying? So in fact, some of the compilations that we look at, for example, compilation of a quantification into a big conjunction only makes sense in finite worlds and known initial worlds where all the objects are known upfront. Okay? And similarly, compilation of this action into two other actions of normal strips type is possible as long as you know initial state is completely specified. Okay, how about this? PRQ, RRJ. So the top is fx, bottom is preconditions. I hope that's what I used it. In fact, actually used it there. No, that's correct. That's what I used it here. Preconditions here, fx here. Okay, so can I do an action A1 which PRQ is its preconditions and RRJ are its fx, is its effect. What? It's not. It's more than that actually. RRJ essentially means it's a disjunctive effect. That means this action is no longer deterministic action. It's no longer deterministic action. It's a non-deterministic action. That means in the atomic case, you essentially have ones in multiple places. So if you do that, then you are out of classical planning. So disjunctive effects are not allowed in classical planning. Once you start allowing disjunctive effects, that means you are gotten out of classical planning. Okay? Now, you all know that P implies Q is nothing but not P or Q. Right? So, today I have said R implies J there. Okay, that's what I said here, right? These are usual slight complications. I mean, that people get confused about. You may not be getting confused, but on the other hand, you're looking so silent that maybe you are confused. So I just said you cannot do R or J because that's a disjunctive effect. I did allow, previously I already allowed these kinds of effects. Those are called conditional effects. But then, but you know that R or J is nothing but not R or J. That's a disjunction. So what gives? There must be some, yes?
The conditional effect has a direction, whereas the disjunction you could interpret it as a conditional either way around. So
yeah, better way of
so
saying
if they're
it.
both false, then you don't know which one to make.
No.
That also could be not J implies R.
What?
I mean, couldn't that also be not J?
No, there is a simpler idea. Yes, sir.
Well, here, the rule says if the rocket's at Earth, then that universal quantification has to be satisfied, but that could mean that one of the unloaded boxes just appears on the moon, and that implication will be satisfied. So to speak.
Yeah, no, I think you guys. So okay. So what? Okay, let me give you the answer, and then you can see, why you may have gotten confused. The interesting thing, given an action, there are two situations with respect to that action. And go back to the old situation calculus. There's a pre and a post. Okay? Conditional effects are total syntactic sugaring, and they are combining a pre with a post. When I say R implies J, I'm not talking about R and J are in the same world. If R were true in the world before, J would be true in the world after. Whereas, so normally when I say conditional effect, I completely mean that the antecedent is true in the previous state, the consequent is true in the next state. Okay? Whereas if I just write a normal disjunction, I mean that disjunction is true in the post state. And if it is true in the post state, that means it's a disjunctive effect. Okay?
It's strange. The implication doesn't really mean actual implication.
Exactly is my point.
Causes.
Exactly, it means. That's exactly the point. So that's, if those of you who are, who thought about this, I guess there's causal calculus, for example, that, Chitta looks at. So the point is, you would see this as the notation for conditional effects. There's a big implication sitting, except it's not the normal implication at all. It is, if this is true before, then it will cause this in the post state. Okay? And in fact, obviously, so that means J implies KRW, that would be a conditional disjunctive effect. Okay? You are completely right that don't think of this implication as logical implication, it's causes. Okay? But it's worth noticing the difference. Okay. That's it for that. That's it about that. There was a question. So as I was discussing this, I sort of mentioned that already that this can be essentially, if I start with a step like, if I start with an effect like this, which has quantification and I don't like quantification, I can write it as a big conjunction. So it will become a big partial assignment. Okay. I also know that if I have a P or Q as the precondition, I can compile it away and it will become normal strips actions. Now the one other thing that is left is what happens to conditional effects. Can I compile conditional effects away? If I have A which says if P then Q, if P is true before then Q will be true after, can I compile this out into a set of actions without conditional effects, but just have normal preconditions, normal effects? Obviously yes, right? Because you can write A and say P is true, in which case Q would be true. Okay, so there is like a P and not P. Okay, and then there is another effect which says not P, then that doesn't have the effect Q. It has nothing, no effect. It doesn't have not Q effect either. Okay, there really are two variations of this action. One which has precondition P will give you this Q, unconditional effect Q, and one which has precondition not P and it will give you nothing. It doesn't guarantee anything, essentially. Now, suppose I have R implies J and top of P implies Q. Then when you compile, essentially you will have 4 actions because you need to think of a world where both P and Q are true, another where P and Q are false, another where one is true, the other is false, other is true, the first is false. Okay, so you can compile, but the number of actions will blow up exponentially. And in fact, if you are interested in what kinds of syntactic sugaring can be effectively compiled away, there's actually a very nice paper that I might send you a link to by Nebel in JAIR, some years back, who looks at which kinds of syntactic sugaring can be effectively compiled away in the sense of whether the domain theory will increase exponentially and also whether the plan length will increase exponentially. Okay, but we will assume basically that most of the syntactic sugaring can be compiled away, and once it's compiled away, you'll still get solutions. Okay, so those are all the variations that I talked about. Disjunction, quantification can be compiled away, and conditional effects can be compiled away. So everything can be compiled down to a canonical representation. And yet, one question, of course, is if you do have conditional effects, rather than compiling it away, you might want to make your planner use them directly. And we will mention towards the end of today's class, if I go fast enough, how to change progression, regression, and partial order planning such that they can handle conditional effects directly. Okay, of course. So anytime you are given a planner, most planners, are basically, there is this thing called international planning competition, where since multiple people are working on the same benchmarks, they need to standardize. Okay, and the lowest common denominator is this representation. This is called the positive preconditions strips representation. And most domains are given a formalization in this model. And then there is, if you remove the positive, that means you can have both positive and negative preconditions. So if your domain model has both positive and negative preconditions, some planners don't know how to deal with negative preconditions, because it's not because it's really hard, it's just that they didn't support that feature. Okay, and then some planners may not be handling conditional effects directly. So if you throw in conditional effects in the domain model, then if the planner doesn't know how to support that feature, then there should be a preprocessor which converts it into non-conditional effect version. Okay, so that's the, and since we know that everything can be compiled out into the canonical representation with both positive and negative preconditions. In fact, one interesting thing is, even if you don't really believe that any action worth its name will have anything other than positive preconditions, if you have conditional effects and you compile them away, you will get negative preconditions. Because P implies Q has to consider both P and not P, which is should not be surprising at all to you, but again, some years back, actually people, for the first time, they were forced to support negative preconditions in planners was when they started considering conditional effects. Okay, because otherwise I can always just come up with a formalization of some domain where everything is only positive as a precondition. Okay, so that's the this is sort of some notes on the representation. And then this one is basically talking about whether or not you should support actions directly or in a compiled way. So if you compile it away, then the lowest planners, so clearly from the point of view of the number of planners out there, the number of public domain planners that can actually solve a domain, that number is much higher if you stick to positive precondition strips. As you keep adding, features, more and more planners will basically stop working. Because why? Because they were written by people like you, and your interest is not to support the world, your interest is to write your next paper. And so probably you don't necessarily support every possible feature, except you're only focusing on the things that you need to show something about. Okay, you can easily argue that in general compilation can have actually negative problems, because in some sense it makes the compilation of conditional effects into strips is not that much different from compilation of strips to atomic models. It has some of the same problems. Okay, and to the extent we believe atomic models are not good and we need to deal with propositional models, then some of those arguments will also hold for compiling the other way around. Okay, so you can read that, and basically it's explaining some of the trade-offs in whether or not you want to compile. Okay, the other thing, the last thing about representation that's relevant for the planners that are out there right now is most of them actually support multi-valued fluents. I'll explain to you in a while actually as to why multi-valued fluents became very important, because actually, in fact, I can explain to you. So suppose you have a multi-valued fluent. That means, the multi-valued state variable. We'll use the word fluent to mean state variable. Okay? If you have a multi-valued state variable, you can always convert that into a set of Boolean state variables, right? Now, how do you do it? So suppose I have a state variable S1, which can be either V1, V2, or V3. So then what do I do? To convert this into Boolean state variables, what do I do? Presumably I will say S1 V1 is one variable, S1 V2 is another variable, S1 V3 is another variable. And then I'll just write all the, any action which had a precondition saying S1 must be equal to V1 will now just say S1 V1 is true. What else do I need to do there to make the compilation correct?
Mutual exclusion.
Yes. Okay. So really what I need to do is only one of S1 V1, S1 V2, S1 V3 are true. Okay. Logically, if you have n things and you want to write only one of them is true, okay, you need to write a whole bunch of binary mutual exclusion relations. It's actually a non-compact relation. This is something, jumping ahead, at one point of time we might compare, for example, propositional satisfiability and for the benefit of this guy, IP representation. So in fact, the same problems, there are problems in the world which can be solved either as a Boolean satisfiability problem or as 0-1 integer programming problem. So which one should you use in that case? And there's a whole entire area now called essentially constraint programming community, where people from satisfiability, people from CSP, people from IP come together and try to exchange which pieces of these three essentially independently developed areas should be combined. And one interesting point is this guy knows how to write, if you have n state variables, 0-1 state variables, and only one of them can be 1. At most one of them can be 1. He knows how to write a constraint for that, right? One constraint. Whereas all you guys from Boolean satisfiability have to write a huge n square constraints for all, pairs. And similarly, there are constraints which satisfiability people know how to write compactly that IP guys don't have an easy way of writing. Which is why you have constraint logic programming, where essentially you sort of try to use best of both worlds. Okay, but that's beside the point. For now, until we get to IP, we'll just assume we are living in satisfiability CSP world. Okay, in that case, actually saying either S1v1 or S1v2 or S1v3, only one of them will be true, which is a valuable piece of information that was provided to you here. And when you compile, if you lose it, then it's not so much that you will die. Basically, the actions will normally be written in such a way that inconsistent states cannot be produced. The point is, during search, you don't have this information. So you will figure out this mutual exclusion between this and this, this and this, and this and this, the hard way. Because search fails. Do you understand what I'm saying? So this was piece of information that's available to you right in front of you, but because it's not all that easy to write this, it's not a pair, it's a huge number of mutual exclusions, you tend to wind up rediscovering it. And this is one main reason why people actually just have found that from a search point of view, using multi-valued state variables directly is better than compiling them down to Boolean state variables. That's it. That's the real reason. It's not so much that one is any better than the other. It's just that there is this very simple connection. Okay? And in fact, this idea is also true for the set of papers that try to compare CSP and SAT solvers on the same set of problems. Many problems, like 8 twins, can be written as a CSP problem or a SAT problem. Which one should you write it as? Now, unfortunately, most of these questions are never asked in complete vacuum. Okay, when I ask this question, I also realize that CSP people tend to be very laid back. They'll write like one solver every 10 years. Okay, and SAT people are like eager beavers. They have a SAT competition every year, and every year they are improving SAT solvers. So if you're trying to bet today, if you're trying to bet on which ones, then I probably am going to bet on the SAT guys, because even though a multi-valued variable, when compiled down into a Boolean variable, you lose some structure, these guys are eager beavers. This is like RISC versus CISC. Okay, RISC computers, you can come up with a new version every year, whereas CISC computers, they were not able to keep up and they just went out the window. And the OR guys, the IP guys have it even better. They just say, we won't even bother making a solver ourselves. Okay, again, these are all caricatures, but basically we'll depend on ilog. Ilog, whenever it feels like its stock value is falling down, they'll say one more version of IP solver. And so you just all buy that, and it's like $1,000 a shot or something even for students, and then you run your same programs on this IP solver. Okay, they're all solving the same sort of problem. There's a big intersection between CSP, IP, and SAT. But microcultures are different. SAT guys just keep writing better and better solvers because they have a very simple language to deal with. Okay, CSP guys much less eager, and IP guys have outsourced it to France because ilog, I think, is headquarters in France. Okay, so again, coming back to Booleans, we would consider, in fact, in all the discussions I will do, I will essentially act as if the Boolean variables are really two-valued variables, so that you should be able to do it with 3-valued and 4-valued. Okay, so this is one of the reasons why I would not agree to make the distinction between add versus delete, because what's delete in when you have 3 values? So like basically when you have 3 values, you say make sure that this guy doesn't have value v1. What does that mean? It has either value v2 or value v3. Which one? Right? Okay. So that's an important thing, you know, and in fact, one of the things that, given that most, as I said, most domains for the IPC planners are given in positive strip speed conditions, okay, positive strip speed conditions, then, so in fact, the PDDL that I think I mentioned it to you the other day, but, you know, these action descriptions look something like this. Okay, so here you have precondition, and it's clear object 1, on table object 1, arm empty, block object 1, effect, and there are some knots, and then with the knots are essentially the delete versions, and the other one is a positive effect. Okay, so most domains will have a formalization in this, and some also have formalizations in conditional effects. Some, a fewer of them have formalizations with quantified conditional effects, and so on. Okay. So the question, of course, is that if all of them are thinking in terms of Boolean variables, is that because the world does not have multi-valued variables? Actually, it does have multi-valued variables. Somebody sat down and converted it in terms of Boolean variables. And so when I said that most current planners use multi-valued fluents, in essence, what they're actually doing is they're starting with a description which has converted a multi-valued world into a Boolean world, and they are, before the planner's search starts, they run a preprocessor to try and at least capture some of the obvious multi-valued fluents in them. And so then they make an intermediate representation, which is what people should have actually given if if in fact you're writing the best model for this. Okay, so then they get that, and then they'll start the planner off. Now the question, of course, is if I have a bunch of Boolean variables, what might they be doing to get the multi-valued fluents out of it? One idea is there are ways in which you can compute these mutual exclusion relations. So if I have a bunch of propositions, P1, P2, P3, P4, P5, P6, and then I'll put a link between 2 of them if it is the case that there is a mutual exclusion that I computed between them. Okay? Now, if I have those 3 links, then that's a clique. If it's a clique, that basically means it's really a single state variable with 3 different values. That's how they'll actually recompute it upfront. Before the search starts, they will find these are eternal mutexes, right? In fact, when you read the graph plan part, right, and then you know that sometimes 2 fluents may be mutually exclusive for small lengths, for a given length of plan, but will become possible together for longer lengths of plan. Okay, those are called temporary mutexes. An eternal mutex is these 2 fluents will never ever become true at the same time. Okay, now this kind of an analysis will find mutual exclusions, eternal mutual exclusions between pairs of variables, and then find the cliques in the graph, and say for each clique, call it a Boolean, a multi-valued state variable of the size of the clique. Okay, and then run the planner which uses this representation. Okay, so that's basically what is being said here. I've written it down, but I'm saying it, it's easier to draw pictures on the board, write text on the slides. Questions? Yes?
Isn't click finding itself an expensive operation?
It is. So one of the interesting things is these guys, one of the things, suppose it turned out that actually there is one like this and there is one like this, and maybe they did not find that there was one like this, right? And if you put that one too, then it would have been a click. Their limited analysis did not let them find this link. So they would actually have taken something which is a 4-valued state variable, and split it into one 3-valued state variable and one Boolean state variable. But it's still better than having 4 Boolean state variables. This is something that comes across the board. Okay, so these things, as long as it's not going to affect the soundness. Remember that if you started with Boolean variables, all that would affect is your efficiency. Soundness will never be affected, because as long as you wrote your actions correctly, it will never actually generate inconsistent states. It's just that the mutual exclusions that would have been obviously staring at you when you realize it's a 4-valued state variable and it can only be one value at a time, you would have to figure that out the hard way during search. Now, if I want to reduce that amount of time wasted in the search, I can spend a little bit of time doing this, and that will help me later. In fact, another idea, because we're talking about this, there's another idea. In fact, pretty much, once you start talking about any search improvement ideas, all of them have this property that you'll spend a little bit of time to improve a whole bunch of time in search. And so, for example, in those of you, all of you have read planning graph stuff in the chapter, right? Suppose I ask you the following question. So you also read that planning graphs, for example, in planning graph you do mutex propagation. Okay, it finds the mutual exclusions between pairs of entities. Okay, and then when a mutual exclusion doesn't change at the level of level, I get to do this because you read that chapter, even though I haven't formally talked about it, right? So when this doesn't change at the level of condition, that means there are 2 levels where the propositions haven't changed and the mutual exclusions haven't changed, then you stop. At that point, whatever mutual exclusions are there, those are eternal mutual exclusions. My question is the following: have you found all eternal mutual exclusions that are true for that domain? Actually, no. Because if you have to find every possible mutual exclusion, that's as hard as planning. In fact, most of the sub-problems would be p-space complete. Okay, the planning is p-space complete. Most of these little sub-problems that you're trying to find will also be p-space complete in the worst case. Okay, in the planning graph scenario, the reason it's actually quite easy to show that you will not be able to find all binary mutexes, even all the eternal binary mutexes. Why? Because remember, you're only finding binary mutexes, never ternary mutexes. You're never finding ternary mutexes and quaternary mutexes. Okay, what's a ternary mutex? That means only one of these 3 will be true. Quaternary means only one of these 4 can be true at the same time. Okay, now something might become binary mutex here, but to be able to see that it's binary mutex here, there may be 3 mutex among these and another 4 mutex among a whole bunch of things. Those together imply this binary mutex. And since you are not finding this, you can't find this. In fact, in planning graph, forget about binary mutexes. What is a single mutex? Unary mutex. A unary mutex is a value for a variable that can never be reached. A value for a variable that can never be reached. Does planning graph analysis find you all unary mutexes? No. Why? Because essentially showing that not P can never be reached is showing that there is no plan for achieving not P. Yes, sir.
By never reached, do you mean it's not in the range of the variable?
No, that means you can never reach a state where P will be false. You will never legally reach a state where P will be false. That's unary mutex basically. That's what you're learning, right? So the point is, in fact, this is a lot about planning graph itself. Planning graph analysis doesn't find all the binary mutexes. It doesn't even find all the unary mutexes. It finds a few of them that sort of improve the speed. Okay? And same thing here. It won't necessarily, this analysis, if you are very serious, you could actually spend a lot of time just finding the clicks and that will kill you. Okay? at one more idea which you would read a paper on. In fact, planning graph heuristics are sort of number 2 now. Number 1 heuristics in planning is landmark heuristics, okay? Which is essentially, you know, given a problem, you try to quickly find out what must be states that you have to go through to get to the final goal state. Okay, so I will tell you, for example, that my goal is to go home. And then you will quickly find out, okay, Rao, given your domain, you have a parking lot downstairs as one landmark. And then Mill and University intersection as another landmark. Now, in fact, you could be wrong. Actually, maybe in fact, Mill and University intersection is not a landmark because I could turn like this and go off that way. In which case, I don't have to go through that. Okay, out of parking lot certainly is a landmark, assuming that I don't want to go walk home. Okay, in fact, that also can be changed. If my domain is such that I can fly home or I can hitch a ride, then even parking lot is not a landmark. So you look at the problem, you look at the domain description, and quickly come up with intermediate states that you are required to go through. And use that information to speed up the search for plans. And you'll read a paper on this. In fact, I won't necessarily teach all of it to you, but it's very much at the cutting edge right now. Okay, now the interesting thing is, how hard is it to compute landmarks? Computing the landmarks is as hard as planning, right? To show that I will always have to go through a certain state, you need to show that there is no plan to reach my goal state without going through that state. That means you need to show if there's a particular problem doesn't have a solution. That's P-space complete. Okay, so obviously what they do is they will just greedily find the low-hanging fruit of the landmarks and use them to improve the search. And planning graph greedily finds the low-hanging fruit of the mutexes and uses that to improve the search. And this is a slippery, this is sort of a continuous spectrum. There are planning graph heuristics which don't even bother finding the mutual exclusions. For example, the relaxed planning graph heuristic doesn't even care about the interactions between the actions. It just assumes everything can be done together. And it still has some information about the problem because it at least sees whether, if there are no interactions between the problems, can you reach the goal state. Okay, and and my favorite example of all these cases, which some of you probably, you only said one guy was in my intro to UI class, so I can draw this picture. So if this is so I could spend the analysis, the amount of time I spend computing the heuristic or problem simplification. This is the time that I spend doing that. And here is sort of the time I spend solving the simplified problem. Okay? Now obviously if I spend a huge amount of time finding all the clicks, finding all the mutual exclusions, finding all the landmarks, then I'll sort of have a perfect heuristic, and so solving the simplified problem would be trivial. But then the total time I spent is this plus this. And what I'm really trying to improve is the sum. Okay, and wherever the sum becomes the smallest, that's the amount of pre-processing you should do. And obviously you don't know up front where it becomes smaller. We only guess. In fact, in planning, people used to guess that the sum will become smaller somewhere here. So they would come up with heuristics which would take basically order one time. Okay, in fact, the most popular heuristic in planning is take your state, take the goal state, find the set difference between them. It'll get done very fast. I mean, imagine that's like a 2-line list program as against writing the entire planning graph and checking the mutual exclusions and using that. And it's even harder if you start doing the landmarks and all that stuff. So people would not even try more complex heuristics because they were biased to believe that this is where they are. And if you and your friend and your friend's friend are all trying only set difference heuristics, okay, you'll only be comparing each other in this loser area, and you may be a slightly less of a loser than your friend, and you still get your paper published. And then you need some guy who doesn't believe in the conventional wisdom, who comes and says, hey, I'm going to spend a huge amount of time, significantly longer amount of time doing heuristic, and see what happens. And many of those people, you don't hear from them, because they do this, either their heuristic never actually got computed, or they did compute and they found the total time was worse than the loser's total time. Because you could actually be doing somewhere here, in which case the total time here is higher than total time here. And sometimes you come up with good ideas, which then you prove to yourself, you show to yourself that is actually, in fact, doing the right balance. Then that becomes the wave, and then people will stop doing the set difference computation. You have to pull people, almost drag people into doing more complicated heuristics. Because you think heuristic is supposed to be making my life simple, and if I need to read 5 papers to understand what the heuristic is, what am I wasting my time for? Why can't I just solve the problem? Right? Okay? Questions? Yes?
Isn't this just a special case of exploration versus exploitation?
That's interesting point. I can't answer this in a way it will make sense. It's related, but it's not a special case. Okay? We'll talk about this at some point of time. For example, when we talk, I think there is the UCB, upper confidence bound based heuristic ideas actually are connected to that. It's not exactly the same, they're connected. Okay. Maybe we can talk about it offline, or I'll hopefully bring it up when we get to reinforcement. Other questions? Okay. So, what do we lose with strips actions? I assume enough people here know. All the Chitta and Julian crowd should be thinking, there's this long time back I went to some conference where this guy was wearing a t-shirt which said 20 years of that time, 20 years of research into programming languages and C is the result, ? Okay, and this is what I guess Juyung and Chitta would be saying. 35 years of research into knowledge representation and strips is the result of what planners are doing. Well, I would love for the planners to do essentially better, higher representations, that is the more lifted representations. In fact, those could be your projects. Okay, what happens oftentimes is people who are working in the lifted representations only compare themselves with other people who are using lifted representations. And just as a couple of kids comparing themselves among themselves over set difference heuristic, okay, and one of them will still win, right? Right. And similarly, if you're only comparing yourselves to the other lifted guys, you may not be actually able to answer the question as to whether you are competitive with respect to people who are grounding it and doing better. And the best way to show it is that in the same competition where everybody is using you can use the atomic representation or propositional representation or lifted one. You use lifted search and you won. That's fair and square. That doesn't exist right now. And that's why I mentioned that thing previously, that the longer the Fernando Pereira seems to live, the lower down the Chomsky hierarchy he seems to fall. He knows that there is much better life up there in second order, 18th order logics. But he seems to be mucking around in propositional attribute representations. Every once in a while they'll write a paper saying, oh, what a bad representation, but that's the only thing that seems to be working fast. Okay? And we believe, I think many of the people sort of tend to believe that lifted representations will work, but we haven't figured out how to make them work in a search wise. You can easily say lifted representations are great from a representation point of view. Yeah, I agree that. But if you're going to only use them for the representation and every planner in the world is going to compile them down and do ground search, then essentially it's still reasonable because people don't have to give ground representations in the models. But it's still really not going as far as we need to go in terms of actually combining the reasoning and search together. I mean, representation and search together. Okay, so what do we lose with strips actions? We must write all effects explicitly. For each action, if it is going to change a state variable, thou shalt write that. Okay? So it's not enough in Bloxworld to say that this guy will put A on top of B and assume that anybody who understands Bloxworld understands B no longer is going to be clear. Okay, for that basically means you are in this within the state. You need to do additional theorem proving to compute other statements that will hold. In fact, the original reason strips representation was invented was to avoid that extra theorem proving, essentially. So, because it's somebody else's problem, somebody else tells you exactly what will happen after you do this action, and so you will get the entire description of the state afterwards. Okay, which means modularity is out the window. Okay, for example, if you now written like 3 pages long blocks world description, and then your friend says, hey, now we have these magnetic blocks which can sort of allow 2 blocks to stand on top of them. You know, half a block this way, half a block this way, and they can keep both of them on top. So it's no longer the case that just because you put a block on top of another block, the lower block is not clear. It has space for one more guy, right? Now, you know, your software engineering guys will tell you that modularity is important. Such a thing should be just changed in one little place in the model. Whereas strips representation, you have to change every action. Many actions have to be changed so that this is now compiled in. Okay. Once again, actually, this is particularly sad for AI people, right? I mean, programming people don't care, right? I mean, in programming community, the very fact that C, C++, Java, all these languages are the things that you program in rather than any higher level languages. Java is okay probably. Is that people are paying for your time, and then you just, you know, they don't really care if you do, if you can do programming in assembly language. If it's fast, that's good. Okay, the human time doesn't matter because the boss has already paid for the human time. Okay, but AI people are supposed to care about the human time. You know, we are supposed to care about whether or not writing this domain description would be easy for the human in the loop. And obviously, it's not. You know, it's not easy to write the this thing. So one can of course say that I will allow humans to provide quasi-strips languages where they allow these kinds of intra-state domain axioms. But then I'll convert them into a strips representation where the domain axiom is compiled into the representation so that every planner can use it. Okay, those are kinds of things that you lose by actually going with the strip representation. Leads to loss of modularity is the big point. Okay, let's go through the 3 search methods. In fact, I think I'll do 2 of them and probably we'll run out of time by the 3rd one, which is actually the neat one, but we'll see anyway. So progression, what you do, you start with the initial state, you apply each of the actions, you compute the new state that will occur. There's no, it's not particularly hard to do. And then if any of those states, the goals, you know, assume that in the simplest case, the goals are specified as a partial state assignment. That's the simplest kind of goal assignment. Okay. In fact, obviously, even for classical planning, without changing anything about the staticness of the environment, the deterministicness of the environment, okay, you can still change the goals. You can say, make sure that you reach this final state while touching the following states on the way. Okay, those would be trajectory constraints. In fact, normally those kinds of goals have to be represented over sequences of states, and so you would use LTL sorts of linear temporal logic. Some of you hear about it. We will come to that in the class again. You might use that to represent the goal itself. But for now, we'll assume all that we care about is the final state. So goal is about the final state. Okay? And so you keep going, and if any of these states, the partial assignment of the goal is holding in any of the states, you stop. That's the progression. Okay? And so generic progression planner, not all that hard to start. Write a search, essentially. You know, apply all the actions, get the new states, and then you search the space in any which way. You can use A star search, you can use iterative deepening, you can use IDA star, you can use local search, you can use hill climbing, any one of them. Okay? But basically the space itself is set up by this child generator, this goal. Okay? Now for the regression, that's the other interesting thing, which is actually start from the initial, from the goal state and see if you can reach a place where initial state is already holding. Reach a place where essentially, so you're starting with the goal state. Suppose you're incredibly lucky, then this partial assignment already holds in the current initial state. In which case you say, I'm done. A null plan solves this problem. If not, I essentially sort of somehow take this, regress it over an action, pick an action, regress it over that action, and then that action will give some of the pieces in this, and will transfer other of the pieces for other people to work on. Plus, because I put the action in, its preconditions now become sub-goals to work on. Okay? So then, this is a new partial assignment. If this holds in your initial state, you can stop. This is regression. Okay? By the way, so what I'm interested in this case, I told you my problem. My problem is A and B are on table. A is clear, B is clear, hand is empty. And what I want to make sure is in my partial assignment, the only thing I care about is B should not be clear and hand should be empty. First of all, can you solve this? I mean, that's my usual question because I'm not drawing pictures, right? So can you solve this? Make sure that all of you understand that you can solve it, right? It's only 2 blocks, and I just want in the final state B should not be clear, hand should be empty. Okay, so now when I go from here, essentially regression essentially is I can pick any action and regress a goal state over that, and it does exactly what I said. You know, it will basically give some of the things in it, and it will give the rest to somebody for somebody else to work on. The one thing you want to make sure is if I'm regressing this over put down A, let's say put down A will give me what? First of all, why would I regress this over put down A? Does it give anything? Putting down A gives what? It gives hand empty, right? That's the reason. Okay, so you can use put down A and you will get hand empty. But suppose put down A also, suppose I'm using an action which gives this, but it violates this. Then there is no point in regressing this state over that action. Because this is the very last guy that's going to be there. Remember, now the plan is being grown in the backward direction and it will be executed in the forward direction. This will be the last guy that gets done. And this guy will give this and will remove this,